right, greetings, ninth graders. This is Mr. Rogers, and I'm here to record and share with you the answer key to the Sedimentary Rock Lab here. Let's go ahead and run this thing, and we'll talk through the answers and see if the mistakes that you made slowly start to make some more sense to you as you learn more about how sedimentary rocks work. All right, so hopefully you have your lab in front of you and you've had a chance to look at the different samples. Let's start with question number one. You have an unusual rock here with question one. It's a rock that's made out of lots of other rocks, pebbles and sand and things like that. You can see lots of different shapes, sizes, and colors. And so the question that's being asked of you here is, do you think that all of these pebbles that are inside of this rock, this new rock, did they all come from one single rock source? Maybe some other rock that eroded and then made these pebbles that then joined into this new rock? Or do you feel like they may have come from lots of different rock sources? And most importantly, what are you observing that would support whatever idea you're coming up with? So when you look at this, you notice that, yeah, lots of different sizes and shapes, but most importantly, different colors. And so like this large piece of sediment right here, this large pebble is clearly black. You can see another one down here that's kind of an orangish tannish color, brown. There's another one that's kind of a milky white. And when you start looking at these, you realize that they must come from different rocks since they have different colors. And so, as I always like to say, if there was a professional geologist in the room, their answer might match yours right here, that, yeah, these probably did come from lots of different rocks that eroded, and then all of those sediments were brought together to form into this new rock. They may have even come from different parts of the planet. And you can tell that from the different rocks that are in there. All the different colored rocks obviously then mean that these are different sources. They have different minerals in them. So if you got that question right, cool. Mark it right in that square at the bottom. And if you got it wrong, also cool. Just mark it that you got it wrong and then write this correct answer. And feel free to pause after any of these answers to give yourself time to write down the full answer. All right, we move on to number two. Number two, you had a microscopic view of a sedimentary rock called a sandstone. And with the sandstone, if I zoom in here a little bit, it would have looked very much like this photograph here. You can see lots of round sand grains. So the question here is kind of a three-step question. First part of the question asks, how did these sand grains get so round to begin with? And the second follow-up question is, what conditions would it take to make the sand this round? And then the last follow-up question would be, how long do you think this process, whatever process you're thinking of, how long do you think it would take? So again, looking at the picture, you may be thinking about some of the lab experiments that we did last week with the rock tumbler, where when you tumble the rocks, they tend to break down and smooth out and get more round. And I think that would be a really good model here. That, of course, would be referencing this idea of mechanical weathering. So to tumble the rocks, to get them to hit each other and to break down into smaller and rounder pieces, the conditions you would need would be water, obviously. Water can help to move things from one location to another. Remember, rivers are just as much sediments as they are water. And so the sediments are rolling down the river, they're being transported by it, moved by it. And so, yeah, it seems like watery conditions would be a prerequisite here. Now, the length of time that it would take would be another thing entirely here. Would it be a year? Would it be 10 years, 100 years? I think all of those ideas are probably too short. And I think what we ought to think about is our deep time calendar that we did a week or two ago. Remember, all of these activities that we are doing in this unit, they do connect together. They all kind of fit as puzzle pieces. So when you think about 4.5 billion years worth of time, that concept is called deep time. And I think deep time here would be needed, right? The longer that these sediments are rolling around, the more and more round they could get. And so this process could take hundreds of thousands, maybe even millions of years for it to all take place. And when you have that much time on your hands, there isn't a rock anywhere on the earth that could withstand these mechanical weathering forces, and they will get reduced down to sand, and then even smaller than sand into like fine dust, and then maybe microscopic particles even. All right. So then that brings us to number three, a kind of a boring looking rock here. It's very ordinary. I don't see any pebbles in it, nothing to make it distinguishable. It's just kind of a bland tan rock. And the question asks, why can't we see any pebbles in this rock? And if you kind of take into consideration something we learned about with igneous rocks, remember how igneous rocks could have really tiny crystals, so small that they're microscopic and you can't really see them unless you had a magnifying glass or a microscope. And the same sort of thing could apply here, but instead of crystals, we're talking about sediments. So the answer here is because the sediments are so small, they're microscopic. And that's why sometimes you can see them if they're large enough, but there's nothing to say that they can't be too small to see too. And so, yeah, there's our answer for number three. All right, moving on to number four. This rock here was an interesting one. You would have seen a rock very similar to this, and it would have had kind of some waves on its surface. And so the question state says it says this rock, this one right here, was formed along a shore of an ancient ocean. Interesting idea, but no one was there to see it, so we need some observations. We need some evidence to back this up. So, what observations can you make about this rock that would support that idea that this was like along the shores of an ancient ocean? And I would say here, maybe draw on your own experience if you've ever been along a river or along a lake, especially where waves are washing up on the sandy beach or the sandy shore. You might notice that you get these lines that look very similar to this. They're called ripple marks. And it's just the water pushing the sand around and creating these kind of ridges. You step on it and you could smush it and destroy it, but then come back a few hours later and the ripple marks are back again. And so that's what happened here with this rock. These are ripple marks. And so this rock, after the ripple marks were formed, it in the sand, then the sand became the rock, and the ripple marks were preserved. And if I zoom back for just a second, another cool piece that kind of is associated with this is you can imagine some animal walking along the beach and leaving footprints in these ripple marks. And then maybe those footprints could also get preserved. And yes, that really does happen. There are footprints of animals and insects in sedimentary rocks all over the planet. And so it's kind of cool. Dinosaur tracks, even. And so, yeah, ripple marks are kind of a cool thing there. An ancient beach, for sure. Then, if we move on to question number five, if you remember this one, there was a really large slab of rock here, and it was filled with fossil shells. And the question says this rock was once part of the ocean floor. So, what observations can you make to support that idea? And definitely the fossils, I think, the shells, are one half of the answer. So if you wrote fossils and nothing else, you're partially right. So that means you might need to also mark this one incorrect and then put the rest of the answer that you missed here. And remember, nothing wrong with making mistakes. In fact, that's kind of the point. And you get full credit no matter how many mistakes you make here. So definitely fossils are a part of it. But you notice between the fossils, there are these like patches of gray stuff. Too small to be sand. So instead, that would be mud. And that's the other half of the answer there. So, yes, fossils is definitely one part that you see there that would prove that this was the bottom of the ocean. After all, what happens to animal shells and bones when those animals die? They sink to the bottom of the ocean and kind of deposit along the ocean floor. But the other half would be those tiny mud particles. Here's an actual photograph of the bottom of a current ocean, and you can see the sand and the mud is building up, and you can see lots of remnants of things that are still alive or maybe once were alive. And so both of those things together really prove that rock formed at the bottom of an ocean. Again, rocks can talk. It's kind of cool. All right, so now number six might be a bit of a head scratcher for some of us. In fact, probably for most of us. It's a tough one, it's a tricky one. So here you had a couple different samples. You had kind of a small container with some orange or yellow sand and then some orange or yellow sand stone. That sand came directly from the sandstone. It's falling apart. So it used to be sand, and then somehow it got glued together to make the sandstone, and now that glue is falling apart and failing, and it's returning back into sand. And of course, that also goes along with this other sample that's nearby, which is kind of this stripy rock here. And this one is interesting because you can see some gray and some red, and this is not falling apart. So there's something about this glue that's much better than the other glue. So the question then comes in, what's gluing the particles together in these rocks? How did that glue get there naturally on its own without human intervention? And why are some of these rocks so much more solid and others are crumbly and fall apart very easily? So there's a lot here to unpack. And in my experience, most of the time people can kind of like come up with parts of the answer, but having the full answer is kind of tricky. So you may have parts of this right, and you should pat yourself on the back if you do. But definitely be ready to be wrong on a few of these things and maybe learn a little bit about how you're wrong. So I think the best way to reveal the answer is to show you a very short animation. One thing you might remember, if I just pause this for a second, is of course water is everywhere, right? It's in between sand particles. This reminds me a lot of our groundwater work that we did in Unit 1. Now, something that we learned a week or two ago with some of our water lab things that we were doing is that water is excellent at destroying minerals. It dissolves just about everything. It's a universal solvent. So it's pretty rare that you have water that is just pure and doesn't have something dissolved in it. And of course, when water evaporates and goes away, it leaves behind that mineral that was dissolved in there. And I think at the time we said water always leaves a mess. It's not good at cleaning up after itself. So if I let this play, I think you're going to see the water is going to begin to evaporate. Let's see. Yep, I did hit the play button. The water begins to evaporate, and as a result, you get minerals forming in between the particles. It's the minerals that were dissolved in the water to begin with. And so that's our natural glue. And it's a process that can happen very easily. You have the sediments, they get buried. It gets warm as they get buried deeper and deeper, a bit more pressure too. And the water evaporates and leaves behind the minerals. And so there's our glue. Now, one other aspect of this, of course, is trying to figure out why do some glues work better than others. So if I come back over here and reveal the answer, I think most of the answer is right here. Other minerals are the glue. Those were dissolved in the water, in between the sand grains. When the water evaporated, then the minerals were left behind as the glue. Now, why do some of them crumble easily and others are stronger? Well, if you remember from Mineral Blingo, again, everything connects. But remember the Mineral Blingo game, some minerals were softer than others. They had cleavage planes, which means that they broke apart easily. And other minerals were harder. They were harder to scratch. They didn't have cleavage planes, and so they were harder to break apart. And those would make better, stronger natural glues. So the reason why not all sedimentary rocks hold together with the same strength is not all of the minerals that are gluing them together are equally strong. Some glues are stronger than others. So make sure that you mark that right or wrong. And if it's wrong, put the right answer next to it. All right, so here comes number 7. In my experience, we sometimes get confused on number 7 as well, for good reasons, right? Like it's kind of hard to visualize this stuff. But you have two rocks, basically. We've got this rock A right here, if I can zoom in on it. It's got lots of large pebbles in it, and it looks kind of clunky. Compare that to rock B. Let's see if I can zoom over to rock B. Rock B seems to be made out of smaller sediments and not very many big pebbles. So the question here then becomes, which of these rocks formed in deeper, calmer waters, and which one formed in shallower, faster moving streams? And if you think about it, the pebbles themselves, how easy or difficult would it be to pick up this very large pebble here in rock A before it all got glued together with the minerals? Just imagine it's sand and rocks now. How easy or difficult would it be for the water to pick up that rock there, that large one, and carry it and drop it somewhere else? And I think you probably start to realize with that question, it would take a lot of fast moving water, a lot of water pressure to pick up a heavy rock and move it. So the fact that the heavy rocks are here is kind of an indication of what's going on. I think this animation shows it pretty well too. In this animation, you can see over on the left, we have a shallower stream where the water's moving faster and it's got lots of large sediments in it because it's moving faster. It can carry larger sediments. But as it empties into this larger area, the water is going to slow down because the water is deeper and you can't move it as much when it's deeper like that. And so, what happens with the decreasing velocity of the stream flow is that the heavier rocks begin to drop out. So, the bigger rocks drop early on in the process, and the smaller rocks can make it further out, but then they begin to drop when the waters slow down. So, by the time you get way out to the far end, those waters are extremely calm, and the sediments are extremely small because the only time you can drop small sediments is when the water is really, really quiet and calm. So, looking at the size of the sediments can tell you something about the velocity of the water and the depth of the water. If you saw a rock that was made out of lots of large pebbles, well, then that rock was formed in faster moving water. And the rocks that are made out of smaller pebbles would have formed further out here where the waters are calmer. So, smaller sediments means calmer, deeper waters. So, if we go back to the question, between A and B, now maybe it's starting to click a little easier for you and maybe feeling a little less confusing. Rock A has bigger sediments, which means the water was moving faster, and that means it must have been shallower and not deep because those big heavy rocks dropped there where rock A formed. And so it had to have been moving fairly fast just to get the big rocks to that place to be dropped. Now, when you look at rock B, all of the big rocks are gone. They've already dropped because the water was faster somewhere else. And now we're experiencing calmer waters, and now the small stuff can finally drop where B formed. So smaller sediments mean a slower moving stream, and that would mean deeper, calmer waters. So in a sense, these are kind of like igneous rocks. Remember, the igneous rocks, the size of the crystals, told us about the speed at which they froze and their location, if it was cold or in a warmer place. And here, this tells us something similar, at least in this sense of like what the conditions were like. Big pebbles tell you that the water was moving faster, and smaller pebbles tell you that the water was moving slower. And then you can infer some water depth with that. All right, so now we're getting to number 8, which is probably the biggest, most challenging of all of the questions. But if you start to pull everything together that you've been learning and figuring out with the previous 7 questions and the mistakes you made there, then you have a shot at maybe answering number 8. All right, so where are we at here with number 8? So imagine you're standing in front of a 30-foot tall cliff of sedimentary rocks, and you're looking up at it. And you notice that it's made out of 3 layers. The bottom layer down here, you can see. In fact, let's see if we can zoom in. Here's the bottom layer. You can notice it's made out of lots of large sediments. Then the middle layer looks maybe like it's made out of some smaller particles, maybe sand-sized particles. And then the very topmost layer looks like it's made out of even smaller particles. Like right here, I can see the big pieces are fossils, so critters, dead things, and then the mud in between them. So when you think about this series of rocks is telling us a story. The story that it's telling is this, that there was an ocean that started flooding the land at first, but then over time it gradually got deeper and deeper. Now, what observations can you make that would support this idea? So one of the things that maybe popped into your head, maybe it didn't, is trying to figure out which rock formed first. If you have 3 layers, and you have like the top layer, the middle layer, and the bottom layer, which one formed earliest? If you think about your own like bedroom and you think about like your dirty laundry, every time you throw some dirty clothes down on the floor, they just pile up. If you're looking for a shirt from the beginning of the week, you don't look at the top of the pile of dirty clothes, you look at the bottom of the pile because that would have been something that you threw down there earlier. So this would be the earliest event because you need that bottom layer to form first. And then on top of that, the middle layer formed. And then after that, this layer formed on top of that. So as we look at the sequence then, if I backtrack, the bottom layer What were the conditions like during this first part when the bottom layer formed? Well, the water here would have been very shallow, moving very fast. And how do we know that? Because the rocks are really large, just like from that previous question. So at this point in time, there's water flowing, but it's fairly shallow and it's moving fairly fast and it's dropping just the big stuff. But then later in time, this is forming. And you notice that the sediments are smaller, which means at this point, the water level is deeper than it used to be. So now we're getting smaller particles dropping. And then over time, we switch to this kind of rock. So at the earliest, or I should say the most recent time, the waters are so calm that the only kind of particles that are dropping out are tiny mud particles and just fossils of dead animals that died in that spot. So then this would show that the waters were really, really deep and calm at this most recent level. And so if you're looking for an answer, here's your answer. If you got it right, cool, mark it right. But if you got it wrong, also cool, but mark it wrong and then write the correct answer on here. So for the bottom layer, the big pebbles show fast moving shallow water. So at this point, the ocean wasn't very deep. When this layer formed, smaller sediments, the waters are getting deeper and calmer. So by this time, the ocean has gotten deeper. And then by the most recent time, we just see mud and shells, which is like deep, calm waters. This is like bottom of the ocean, a deep ocean. And by this point, then the ocean is at its deepest and calmest. So we can literally see that the seas or the oceans are rolling in. And of course, if we saw the reverse, if we saw this as the bottommost layer and we saw this as the topmost layer, then the reverse had happened. It started as a deep ocean and then it got shallower. So you can also see when the oceans leave as well as come in. So in Minnesota, we see these sequences. We see the particles getting bigger and bigger in the sequence of layers. So we can tell when the oceans are coming in and we can tell when the oceans are leaving, which is kind of wild because this really does kind of reinforce that rocks do have a story to tell. They can talk and actually tell us a lot about what's happening. All right, that was a big one there. The next few should be a little bit lighter and easier. So number 9, why is this wood no longer wood? And what is it now? And how did it get like this? So this is called petrified wood. If you threw this log on a campfire, it would not burn because it's not wood anymore. Just like the question says, why is this wood no longer wood? And what is it now? And actually, even this kind of relates to something we did earlier. If you remember, we did an experiment with chemical weathering where hydrochloric acid reacted to some of the minerals and like started to break them apart and rearrange the atoms. And so the answer we're looking for here has something to do with that. It's no longer the original wood. It's been converted into minerals. It's literally a rock now shaped like wood. It's what it used to be wood, but it isn't anymore. So after it was buried, the original atoms were replaced during a chemical reaction. So the old atoms were taken out and new atoms like quartz, silicon, oxygen, iron were put in its place. So it literally got changed from what it was originally to what that is now. In fact, all fossils are exactly like this. If you dug up some dinosaur bones, it's actually not bone anymore. It's been turned into a mineral or a rock. It's still in the shape of dinosaur bones or whatever fossil you happen to pull out of the ground. It's in that shape, but it's no longer the original material. And true fact here, if you ask really nicely when I'm back in class, I have some fossilized poop that I've been collecting because I think it's hilarious. Because, yes, I'm that immature. And before you get overly grossed out, what's cool about it is that if it's fossilized poop, it's no longer the original material. It's been turned into a mineral. So it's still shaped like poop, but it's no longer poop. And that's kind of wild and crazy. And some of the fossilized poop that I have, the mineral that it turned into is fool's gold or pyrite, a mineral you might remember from our Blingo game. Again, everything connects together. So yeah, golden poop is in my collection. And like I said, if you ask really nicely on Monday, I might pass some around so you can see them. All right, that's a promise and a threat. All right, let's move on to the final question of the hand samples, the hand specimens. So the very last one that had a rock that you had to look at was this one. So why is this black shiny rock so different from all of the others? And how did it form differently from the rest? This is a very different rock. It's lighter, it's softer, it's a totally different color, and this is the only rock on the earth that if you held a match to it, it would actually burn. And because it's coal. But what is coal? Well, coal is made out of plant material. That rock is made out of nothing but pure plant material that has not been able to decompose and break down. Instead, it got compressed and formed into that black rock there. So that plant material, as I said, failed to decompose, and instead it was compressed and hardened into coal. So if you got that right, cool. If you got it wrong, also cool. But pause this for a second and take a moment to write down the right answer. And of course, the other wild thing about coal is it breaks one of the rules of minerals, meaning that minerals are supposed to be inorganic. But by the time we figured out that coal actually is organic instead of inorganic, we had been using it so long that everyone just kind of collectively shrugged and said, coal is an exception. We're going to let that stay in the realm of rocks and minerals. So technically, it shouldn't be considered a rock or a mineral. But, yeah, it is, just because we said so. All right. Now, the final three questions, we'll probably move through those quicker, like the igneous ones. These don't have hand samples. They're just you thinking about sedimentary rocks and kind of putting things together one last time. So, question number 11. Why are marine fossils, which are ocean critters, why are they so much more common to find than land creatures? And what does that tell you about sedimentary rock formation? The fact that it's very easy to find fossilized shells and it's very difficult to find like dinosaur bones can tell you a bit about the conditions. Sea critters get buried so much easier than land critters do. Think about it, they're already in the watery environment. So something that lives in the ocean, when it dies, it's very easy for it to sink to the bottom of the ocean, get buried by mud, and eventually fossilized. If you're a dinosaur or a human walking on the surface, and a dinosaur dies on the surface, its bones are not necessarily guaranteed to get buried in a watery environment and then get preserved. So there's probably a fair number of dinosaur and other fossils that just never got fossilized because their bones were out on dry land. So every land animal that we've got fossils of died in or near some watery environment, right? Maybe it died trying to cross a river or died near the shoreline of some ocean. And so then its fossils or its bones were able to be fossilized and preserved. So, what does that tell you about the conditions? Well, sedimentary rocks form in watery conditions, not dry ones. So that's why they tend to be, these sea critters tend to be more common, just because they're already in that environment. All right, number 12. What kinds of conditions do you need to make sedimentary rocks? I think by now these questions have made it pretty obvious. But if you look at your answer, compare it to what we've got here, I think it's not going to surprise anyone that you're going to need water. You're going to need weathering and erosion, and you're also going to need sediments, and you're going to need deep time. Those are the conditions that you need. You need sediments, and you need water to make those sediments and to transport them, and ultimately to glue them together, and you need long chunks of time for this process to happen. And those are your conditions right there. And then the very final question is, what are some characteristics you would use to group sedimentary rocks together, and how many categories do you think you could make? So you look at your own answers. You may be surprised. You might have actually guessed some of these. Some of the ones that professional geologists would use, maybe the size of the sediments, since the size tells you something about how fast the water was moving. The type of sediments, the different ways that they form, whether they're made out of dead organic material or made out of just pure sediments. All of those things could be criteria that we use to separate sedimentary rocks into smaller groups. All right, so remember what I said. No matter how many questions you get wrong, you're getting full credit for this, as long as you have attempted some answers on your own and you've corrected it to show that you have been doing the learning here and seeing the mistakes. So if you add up all of your questions that you got right, if you got anywhere between 9 to 13 of them correct, I would say you're at the expert level. You, first of all, pat yourself on the back. You know a lot about sedimentary rocks, or you're just enormously lucky. Either way, kind of cool, right? Um, if, however, you scored maybe five, six, seven, or eight of them right, then I think you would be at the intermediate level. Nothing to sneeze at there, nothing to be ashamed of. Being intermediate is really cool because you're figuring things out. And of course, it's also possible you could be at the novice level. And again, no harm, no foul on that. And there's no shame at being a novice here. Maybe if you got zero, one, two, three, or four of them right, just means that you are on the way to learning here. And like we said with igneous, it's possible that you had like a novice score, but you're not a novice after having corrected it. Now that you've seen the mistakes, you're no longer a novice. You might be intermediate or even expert at this point because it all clicks and makes sense. So um, now you've seen all these things. Do you think you could guess the sedimentary rules that sedimentary rocks follow? That, of course, is going to be our next video that we watch and figure out here together. So before we take out the notebooks and start writing that stuff down, you'll want to make sure your name is written at the top of your lab sheet. And then when the video is done, you can go ahead and turn those into the basket up in the front of the room. And we'll see you for the next video segment. Good luck, everybody.